Hi everyone, Mr. Smith here. In this video lesson, we are going to do some examples applying Newton's laws. So let's get started. So in general, when you're solving a dynamics problem, these are just suggestions. Things you want to do for sure. So obviously, like carefully read the problem, etc., etc. Some of you may like to draw a system diagram. That means like drawing a physical drawing of what actually is going on. And a free body diagram is just where you represent the object with like a point or a small box or something, and then show the forces acting on that box, making sure to assign directions as positive if you're in 2 dimensions in X and Y direction. In questions where there are forces that act diagonal to your X and Y direction, you want to resolve those into components, and then analyze the problem using Newton's second law. And we are going to have problems that have multiple objects. So we may need to draw several free body diagrams, like in step 3. We may need to apply Newton's second law 2 or 3 times, depending on how many objects we have. And then what's left will be either an equation to solve or a system of equations to solve. And we'll have both cases today as well. Of course, whenever you solve a problem, you should just take a second to see if your answer seems reasonable. And thinking about units, etc., etc. Like if you're solving for like an acceleration, and you're dividing, say, a force by another force, newtons over newtons, they're not going to give you the units of meters per second squared you want, right? So, and for those of you taking my course, we're not crazy worried about significant digits at the moment. So let's get started with our first example. A little bit of I just called it getting warmed up. And in this video lesson, I'm just going to kind of do the problems along with you guys. It's relatively early in the morning over here. I'm not even sure. Maybe you can hear my 2 kids thumping around downstairs. So we'll see if I can be error-free today. So a contractor is pushing a stove across the kitchen floor with a constant velocity. So that's important. Make note of that, constant velocity. That's a horrible underline, but we'll go with it. The contractor is exerting a constant horizontal force forward, and the force of gravity is on the stove 447 newtons down. So if we draw a free body diagram of this stove, so in this case, I'm not going to draw a physical system diagram. I kind of suck at drawing, but I think this situation is pretty, straightforward to see. So I'm going to say this is the direction that we're pushing, and I'll call up positive. And I'll say the contractor is pushing the stove across the kitchen floor this way. And the question says that force is 85 newtons. So I'll call it FAP. And this 85 is the magnitude of that force. So often, for me, when I'm drawing a free body diagram, I might not necessarily have the vector sign. I can see what direction it is. It's to the right. And we are told the force of gravity, Fg, is 447 newtons down. So if we think about this problem and that there's a constant velocity, if you think back to what that means in terms of Newton's first law, if it has a constant velocity, it's not accelerating, there's no net force acting on the stove, which means we need 2 other forces to balance this out. Now, the question probably gave you a clue. We have a normal force being applied by the floor on the stove. So I'll just call that Fn for now. And we have friction. Later on in another lesson, we'll explore calculating frictional forces. For now, that won't be really necessary. But I do want to talk about the normal force. So in this case, we are pushing a stove along the ground here, and the normal force is a force that a surface exerts on an object that's in contact with it. So yeah, here our normal force is straight up. But a lot of students come out of grade 11 with the misconception that normal force is always up, and that there is always a normal force. So you only have a normal force if you have an object in touch with the surface. But if you've sometimes my kids sometimes they push their toy cars or something along a wall, right? And if you have something in contact with a wall, then the normal force would be, it's always perpendicular to the surface. It could be pointing straight out. Or if if you're in a room that's low enough, you can touch the ceiling. If you had an object and that object and you're pushing it up against the ceiling and it was in contact with the ceiling, then the normal force would be straight down. So like in this case, gravity would be going straight down too. So the normal force doesn't have to point up all the time. Here it does, because the floor is it's along a floor. And the normal force and gravity don't have to be in the same direction as well. So keep that in mind moving forward. All right, so let's solve our problem. And as I mentioned, we're all come from different backgrounds, many ways to show work for this. So we're doing part A here. A common theme when doing dynamics problems in 2 dimensions is that you're going to have to analyze things in the x direction and the y direction. And often it makes sense to analyze things in the y direction first, because often you'll be wanting to calculate a friction force, and often that involves finding the normal force. So it's just a good habit to get into. Doesn't hold all the time, but yeah, often analyzing the y direction is useful. And the sum of forces in the y direction, and this is one way of writing this out. Sum of forces in the y direction equals mass times the acceleration in the y direction. But we know that the motion of the object is to the right? The motion is this way. It's not accelerating at all, let alone in the y direction. So this is equal to 0, right? And so what we have is that our 2 forces have to balance out. And I chose up to be positive. So the normal force, and then I'll subtract gravity because it's going down. So I'll take care of that with that sign convention, negative, equals 0. And so the normal force in this case equals the force of gravity, which makes a lot of sense. So the normal force in our problem perfectly matches gravity, 447 newtons. And that is always the case when you have a horizontal surface and there's nothing else going on with the problem. Now, if you can imagine, say instead of applying a force to the right in our diagram, if you can imagine that the contractor, say, pushed down and to the right, well, now you would have an extra little bit of force in the downwards direction. And to keep the sum of forces being balanced in 0, you'd have a larger normal force. So Fn doesn't always equal Fg. It does in this case because the normal force and Fg are the only 2 things going on in the y direction. All right, so let's look at B. So determine the total force applied by the floor on the stove. Now that total force, they say total because there's actually 2 forces that the floor is exerting on the stove. One is the normal force, that contact force, and then it's applying a force of friction as well. So we actually want to find out what that force of friction is, and we get it in a similar way. Sum of forces in the x direction is equal to mass times the acceleration in the x direction. And again, we know that's equal to 0, right? Because the object is moving at a constant velocity. And so I chose my forward direction to be positive, so positive FAP. And I might just write this in a slightly different way just to illustrate like in the first part here, why I have minus FG. So we know sum of forces, we're adding the forces together, but FF is in that negative direction. So minus FF equals 0. So that's why I just do Fn minus Fg. I find that to be just more direct. And if we just solve this equation for FF, it's, no surprise there. It's just like the y direction. Those two forces have to balance. They must be the same in magnitude and opposite in direction. So the force of friction here, 85 newtons. So I have a second slide here for us to finish this problem off. We're going to determine the total force. So we had a smaller friction force acting to the left and a normal force acting up, and that was 85 newtons and 447 newtons respectively. And what we're trying to find is that total force from the floor. So the question is calling this F floor. And yeah, we're old hats at this. We're going to find the magnitude using Pythagorean theorem. We're going to find the angle using tangent. So let's find that. So the magnitude of this force using Pythagorean theorem, 85 squared plus 447 squared. And tan. So as an aside, as we're doing this, I probably could have done these ahead of time and saved myself a bit of time and just kind of like, clicked through my solution and unveiled it a little bit at a time. But I actually just prefer just to, do the problems along with you guys. Just kind of keeps me sharp and keeps me engaged. Might make the videos a tad longer than they have to be, but it helps me. It just helps me as I'm teaching. So I got about 79 degrees for the angle above the horizontal. And I got about 455 newtons for the total force, 455. So the force at the floor, the total force that is exerting on the stove is 455 newtons, and the direction is 79 degrees above the horizontal. If you want to say above backwards, that's fine. Or if you just want to say above horizontal, I get that too. But yeah, so not a crazy involved problem. We drew a free body diagram. We established which direction is positive. We set up Newton's second law, and we solved the resulting equations. And in this case, they're pretty easy to solve. No big deal. Did a little bit of component stuff together to find a total force. So I thought that was a good little warm-up problem to start with. Let's continue. Okay, so here we have a system with multiple objects. So we have two sleds connected by a horizontal rope with sled A in front of sled B. And sled A is being pulled forward with the horizontal rope, and we have the tension there. So I'm going to draw kind of I think for this one, I'm going to draw almost a little combined system diagram and free body diagram. So I'm going to call this one sled A. So sometimes if I have multiple objects, I just might write MA for that's like mass A, and this is mass B. Of course, you are free to do whatever you like, whatever makes you feel comfortable. And we've got a rope joining these, so I might just draw the rope. That for now isn't representing a force. That's just illustrating they're connected. And what are all the forces we have going on here? And so we have for mass A, we have it being pulled forward by some tension force, which I'll just call FT1. I'll call that our first tension force. What else do we have going on? We have force of gravity. So I'll call that FGA. But sometimes I might just actually, replace FG with, I know that for the weight force of gravity is just the mass times g. So I might just write that in right there. We have a normal force, and the question says we have some friction. So maybe I should actually choose my direction to be positive. So I'll choose up and right again. The sled is being pulled by this rope to the right. And so the first friction force, I'll call that FFA. It's pulling it back and left. And there's one more force too. The tension in this second rope, and this is a different rope, right? The sled is being pulled forward by one rope, and we're given that tension 29 newtons. This is a different rope, so the tensions can be different. So I'm going to label that different tension as FT2. Okay, and that completes the free body diagram for mass A. For mass B, we have force of gravity, and I'm just going to go right ahead and just do MBG. I should probably call that FNA, because then this guy has a different normal force. FNB. We have the tension that's pulling mass A to the left. That same tension will be pulling mass B to the right. And we have friction for sled B, but it's a different force of friction. All right. We've got our kind of two separate free body diagrams, I think illustrating the problem. So now let's get to using Newton's second law to analyze the problem. So we're asked to find the acceleration of the two sled system. So that's kind of a clue. And in cases like these, where you have two objects that are connected together and they're moving with the same acceleration, you can often treat them as a single mass. So for part A, I'm just going to make sure my next slide, I have a second slide ready for this work bleeds over. So for part A, let's actually draw a kind of a free body diagram for this two sled system. If we were to treat them as like a single mass. So what we would have is we'd have some force of gravity. I'm just going to call that big M times G. So that's their combined mass. We'd have some different normal force. I'll just call that Fn. And we have the rope, the first rope, pulling them to the right. And we would have the second rope pulling them. Oh, excuse me. That's it. It's friction that's acting back the other way. So, much like if you're in your car pushing on the dashboard or pulling the seat in front of you, you can't affect the motion of the car. It's the same way that this FT2 and this rope in the middle isn't going to affect the overall system acceleration at all. It's kind of like an internal force. So the other things we have going on, acting just in the opposite direction, are these two tension forces, these two friction forces. We had an FFA and an FFB, we called it. So that's everything going on there. And we know the object is accelerating to the right. There's actually no need for us right now to analyze the y direction. We can just look right in the x direction here. Go right ahead. So the sum of forces in the x direction equals mass times acceleration in the x direction. And I might actually just change one thing here. Because we're looking at the entire system, and I've called that big M, I'm just going to put big M here. So big M referring to their combined masses. M equals MA plus MB. All right. So let's set this up. So I've chosen to the right to be positive. So that means I'll have FT1 pulling right, and then minus FFB minus FFA pulling left equals big M mass times acceleration in the x direction. And we know every single one of those things. So I prefer just to solve for what I'm asked to find, and then I'll plug in afterwards. But if you would prefer to plug in right away, not a big deal. So we're going to squeeze this in here. So the first tension to the right was 29 newtons. And the two force of friction on A and B respectively, I guess I put B first. So that would be -8, -9. And their combined masses would be whatever 6.7 plus 5.6 is. And the last thing we can do is do that calculation. So 29 minus, that'll work out to be -17, divided by, that looks like 12.3. And so we get about 0.98 meters per second. And in the direction, we'll just say forward. Oh yeah, and you know what? This question just asked for the magnitude. So obviously it's forward, but we're good. We can just stop right there. Cool. So we've done part A. It asks for a system acceleration. So sometimes you can treat both of the objects as one by adding their masses together. But you can only do that when they are moving in the same direction. Later on, we might have examples where we have, say, some kind of pulley system. Like so. And, you know, this pulley system, the mass here, if it's heavier, might drag this one kind of off of the edge. But they're accelerating in different directions. So even though they might accelerate with the same system acceleration, because they're in different directions, we won't be able to combine those into a single mass and analyze the sum of forces. But here we could. All right, on to part B, the tension in the rope connecting the sleds. So the important thing here is, so now that we know the acceleration for the whole system, we individually know that mass A and mass B are both going to be accelerating at that speed. And we know what FT2 is, or sorry, excuse me, we know what FFB is. Maybe I'll even just like, so we know FFB. We know the system acceleration, right? We got that. And so the only other thing, if you're just focusing on mass B, the only other thing unknown in that horizontal direction is FT2, right? And that means we can find it. So I'm going to go to my second screen here, and you guys don't have to do this because you should have it just on your page, but I'm just going to quickly redraw a free body diagram just for mass B. So this is Fn for mass B. The only tension force acting on that one is FT2. And we have the friction force, we call that FFB. And yeah, we're looking for the tension in the rope connecting the sleds, T2. So we actually don't care about the vertical direction here. We're not going to analyze the y direction. We can just go right to sum of forces in the x direction equals mass times acceleration in the x direction. And in this case, we're just focusing on mass B, but its acceleration is the same as the system acceleration we got before. So FT2 minus FFB acting in the other direction equals MB times AX. And if we look at that equation, we know everything except FT2. We can solve for it. FT2 equals MB times system acceleration plus that force of friction on B. And let's just plug stuff in. So mass B is 5.6 kilograms. System acceleration we got was 0.98. Just going to double check that, 0.98. And the force of friction on mass B was 8 newtons. 5.6 times 0.98 plus 8. Nice. 13, basically 13.5 newtons. And we've got it, the magnitude of the tension between the sleds, 13.5 newtons. So we got it. Just going to double check that I got that one. Yeah, so 13.5 newtons. We did a pretty good job, I think. So that was our first kind of example of a multiple system, multiple object system, where, in one case, in part A, it made sense for us to treat the system as a whole and both objects as a whole. But in part B, we had to analyze one object individually once we had that system acceleration. Notice that we wouldn't have been able to do this initially because then we'd have two unknowns, ft2 and the acceleration. All right, let's move on. We're going to look at a pulley example. So I think I actually have a system diagram here. So we have a loonie and a dime on opposite ends of a thread. And that thread is put over a bar, and we've got a cross section of that bar. So you can think of this almost like a pulley. And since the loonie is heavier, I think we can all visualize that if we release the system and we ignore friction, that the loonie will go down and the dime will go up. So unlike the sled question, this question that has multiple objects, they're not accelerating in the same direction. So we're not going to be able to treat those as the same object. We'll have to analyze each one separately. However, the magnitude of that system acceleration will be the same for each. If the loonie is accelerating down at 1 meters per second squared, the dime will be accelerating up at 1 meters per second squared. And we won't worry about what happens when the dime actually reaches a pulley. But yeah, important thing here is that when we do pulley problems, we ignore friction between the pulley and the thread. There are ways to deal with it, but they're a bit beyond the scope of this course. All right, so in questions like these, with multiple objects, a great first step is just to look at the free body diagrams for both objects. So we have the loonie. I'll call that a little ML. And what's going on with the loonie? We have a gravitational force going down. I'll just call that MLG. No normal force, right? There's no surface here that the loonie is in contact with. The only other force acting on the loonie is the tension in the string, pulling it back up. And there's only one string in the whole problem. So I'll just call it FT. That's all we have going on. And in this particular problem, let's choose, it was mentioned earlier in those guidelines, but it's really often in your best interest to choose the positive direction to be the direction of the acceleration. And the loonie is going down. So we're going to choose down to be positive. That's the way it's accelerating. And if you want to even put an A to illustrate that I know that it's accelerating down and I'm choosing that way as positive, you can do that. I think I'll just do side by side. So those are two separate diagrams here. So we have the mass of the dime. So we have, that should be mass of the dime times G. And we also have this tension force acting up. The difference here, though, is for this free diagram, and when we analyze this using Newton's second law, it will make more sense for us to choose up to be positive because that's the way the dime's accelerating. So this may be a new idea, maybe not, depending on what you did in your grade 11 course. But for some, it might be the first time where we've got a system diagram with two objects accelerating in different directions, but they have the same acceleration. So that's it. That's all that's going on in this question. So we're now ready to analyze. So I'm just going to analyze mass L. So the sum of forces, and you could say, in this case, we only have forces acting in one direction. So if you want to put Y, that's cool. I might just put sum of forces. But I think maybe for consistency, like our last example, I'll put sum of forces Y equals the mass of the loonie. And I'm just going to put A. So A is just the system acceleration. It's the magnitude of the system acceleration. So yeah, I'll just use A for this one. And so what do we got? So for that one, we have ml times g in the positive direction minus the tension force equals mla. And there's two things we don't know, actually. The two things we're trying to find the problem. We want the acceleration and we want the tension. So there's no way to solve this equation for either one of those right now. So we'll maybe just put a little pin in that for now, and just down below, and I'm going to leave a bit of space intentionally. So down below, for the dyne, analyze Newton's second law. We have the sum of forces in our y direction there equals the mass of the dyne times A, the same system acceleration. And this one's a bit different because this one, I have my tension force is in the positive direction and gravity, md times g, acting down, equals md times A. And again, in this equation, two unknowns, ft and a. But luckily, in your grade 10 math course, you guys learned how to analyze equations with two systems with two equations, two unknowns, traditionally called a substitution and elimination are the two methods you guys have. So either one of those will work good for this one. So if I call this equation 1 and I call this equation 2, I can solve that linear system to get the two things that I don't know. Now, I prefer to leave things in a general sense, but if it helps you to say plug in ML, to plug in G, to plug in ML, and just have the numbers, that's okay. So for this problem, I think I'm in the mood to do some elimination. The reason I'm going to use elimination is because I have a negative FT and a positive FT. So I know if I add those two together, I'll get 0. So I think that sounds pretty good. So I am going to go to my second slide here. I might have to jump back and forth, but you guys should have everything on the same sheet there. So if I add those two equations, what do I get on the left-hand side? I'll have MLG and I'll have subtract and minus MDG. And the FT terms will go away because I'm adding negative FT and positive FT. So they're gone. Here we go. Now, you know what I might do is, at least just for this one, I might just show like everything. So we have MLG. If you feel really comfortable with your math skills, then you can just maybe skip this step. But I think what I'll do is I'll show him adding both of the left-hand sides here, minus MDG. And then I'm adding the things on the right, so MLA plus MDA. And when we simplify things, so those cancel out, right? And we're left with MLG minus MDG equals MLA plus MDA. And the tension force is gone. The only thing in this equation that we don't know is A. We can solve for it. So I'm going to do this in 2 steps. But again, if you can shave off a step, that's really good. So I'm actually going to common factor the G here. I'm left with ML minus MD. So we are relying on those grade 10 math skills a bit. Common factor the A, ML plus MD. And we get this cool, tidy little equation for A. G times ML minus MD divided by ML plus MD. So this is cool because if we were to change some parameters of the problem, say make it a quarter instead of a loonie, or say take this contraption and move it to the moon where G is different, we wouldn't have to resolve the problem. We would have an expression for the acceleration, just plug in our new values. So I might be a bit naughty here and just plug things in. Just might write a couple equal signs per line. So 9.80 meters per second squared. Being mindful here, those masses were given in grams. So we do need to write those in kilograms. So 6.99 grams is 0.00699 kilograms minus 0.00209 grams divided by the sum of those two guys. Yeah, so as we're finishing, I know I've mentioned it, but yeah, I mean, I showed a lot of steps here with the math just because it's our first example and just trying to, make sure people can follow along. But if you are comfortable shaving off a step or two, by all means, you can do that. 9 plus 0.00209 equals. So I got about 5.3 meters per second squared for my system acceleration for part A. So just going to double check. I have this question written out, just kind of roughed it out. Yep, that seems good. Let's look at B. So actually B is not so bad now, because if we go back and look at our equations, equation 1 or equation 2, we actually now know the acceleration, which means any one of the equations will be able just to solve for ft. And I might look at equation 2. So equation 2 looked like this. We had ft minus mdg equals mdA. And if I solve for ft, I get mdg or mdA plus mdg, or I'm just showing an extra step here. It might save a bit of calculations if you common factor out the md. But now we're ready to find that. So the dime, 0.00209, and then 5.3 plus 9.8 should give us that tension force. So 5.3 plus 9.8, 15.1 times 0.00209. And so I got pretty small tension force, 0.03 newtons for FT. All right. And actually, in hindsight, looking at the question with 2 decimal places, I probably could have kept that as 5.29 and then maybe had a bit more of an accurate answer for FT. But I don't think it would have changed. It would have been around 0.03 newtons. But as I said earlier, talking with you guys about the course, I'm not too concerned about significant digits for now. All right, so we looked at our first kind of pulley problem where we had multiple objects accelerating in different directions, but they had the same system acceleration. We're going to do one last example. We're going to tie in Newton's third law and motion. So we have, I think this is I have a diagram. So we'll have to draw a diagram for this one. So we have a family at an indoor skating rink. So we have children along a line facing one end of the rink and their parents behind them. And if you think about being on ice, and if you can imagine no friction as well, we all probably have this experience somehow. But if I push my friend on ice, my friend is going to go away, but I'm going to move backwards too a little bit, right? Because of Newton's third law. I'm exerting a force on them. They're going to exert a force on me. And if there's no friction or anything, that just means like we're both going to move away from each other. And maybe you can predict if one of those persons is an adult and one of those is a child, maybe you can predict via Newton's second law which one of those is going to accelerate away faster. So let me do a little free body diagram here. So I'm going to call this for the daughter, I'll say MD for the daughter. And I'm just going to draw kind of close by capital M for the mother. So what's going on with the daughter? So we've got force of gravity for sure, mdg. The daughter is now on a surface, the ice surface, so there will be a contact force, a normal force. I'll call that FND for the daughter. And let's say that the mother pushes from where she is. The mom's there behind the child. The mom's going to push with an applied force to the left. What do I want to call that for subscripts? I might just call that FMD. So the force of the mom on the daughter. So you could call that whatever you want. You could call that F app from the mom, like comma mom, like whatever you want to do. And there's no friction. So that's actually all we have going on here. The daughter is going to move in the left direction, at least according to my diagram. So I'll choose left to be positive. And we have a similar diagram for the mom. So we have mm times g. The mom will have some different normal force, Fn, capital M for mom. And the force of the daughter on the mom. But the key idea and the mom will be moving to the right. So I'll do that. But the key idea for this question here is that the bridge between these two, this applied force, FMD and FDM, from Newton's third law, they're the same force, at least the same magnitude of force. So I think we should be able to squeeze all this in one. So for A, we're not really concerned with the y direction at all. We can just get right going. So the sum of forces in the x direction. Now we're doing the daughter's acceleration. So we'll look at the daughter first, and times A, and I'm actually just going to call this AD. I won't call it A here because the daughter and the mother will have different accelerations. And so I don't want to have an A for one and an A. I think this just makes sense. And the only force we have acting in that x direction is that applied force. I called it FMD. MD AD. And so the acceleration of the daughter is that applied force divided by the mass of the daughter. And I think we can squeeze this in here. So the mother pushes the child with a constant applied force of magnitude 56 newtons. So 56, it's newtons and it's kilograms. So I know that meters per second are going to come out for 19 kilograms. 56 divided by 19, pretty close to 3, I think. Yeah, we'll call that 2.9 meters per second squared for the daughter. Got it. I'm going to go up here for B. For the mother, we're doing basically the same thing. Sum of forces in the x direction. This time we're looking at the mother, mm, and the acceleration of the mother. I'll call it am. The only force we have in that direction is the applied force. We called it FDM equals mm over am. So it's basically the exact same process as the daughter. We have FDM over mm. Let's plug our stuff in. 56. But because the mother is bigger and we have the same force, from Newton's second law, the acceleration is going to be a lot less. And that's 61 kilograms. 56 divided by 61. About 0.92 meters per second squared. Great. So yeah, that makes sense as we talked about. If the child is smaller, they should have a larger acceleration than for the larger mother. And now we can find out the maximum velocity of the daughter. So we say maximum velocity because this applied force is going to be applied for 0.83 seconds. So this child is going to accelerate for 0.83 seconds. And once the mother is done pushing them, once that 0.83 seconds are gone, the child is just going to be cruising on the rink. And, they're not going to be speeding up. That'd be pretty weird. If we ignore friction, they would continue along at the speed they reach. But we know eventually they're going to slow down. So that's why it says maximum velocity. So I think, I think I can squeeze it in here. We're going to risk it, guys. We're going to try to squeeze this in here. So what do we know? Acceleration of the daughter, 2.9 meters per second. Daughter is at rest initially, lined up along the line. And for a time, oh yeah, we can squeeze this in. For the time is 0.83 seconds. So we got a nice convenient kinematics equation, one of our big five that just gets us right there. V1 is 0, V2 equals V1 plus A delta T. So we're accelerating at 2.9 meters per second for 0.83 seconds. So it makes sense that the final speed should be just under 2.9. But 2.4 is that maximum velocity reached. Yeah, and we're just looking for the magnitude, so we understand that according to our diagram, it would be to the left. All right, so we got it, guys. 4 examples, bit of a longer lesson, but not a lot of heavy content. It's just, you know, getting back in the rhythm of things, applying Newton's laws. And it's my hope that, you know, maybe most of that was not really new to you and you're feeling pretty comfortable, which is great. And if it was feeling kind of new to you, maybe you want to, you know, take a moment if you have these copied down and just kind of digest everything and maybe go back and watch. And if you're unsure of something, and of course, send me a message too if you want any clarification. Should say too, if you notice any mistakes, you got to let me know right away so I can get a post up and fix them. What's next? So in our next lesson, we're going to briefly review how to calculate a force of friction. In the example we did way back with the sled, the forces of friction were just given to us. But if that's not the case, how can we calculate force of friction? So we'll briefly review that, do a friction example or 2, and then we're going to analyze a system with 3 objects. So that should be fun. So yeah, our next lesson, a bit of combination of maybe some review and just maybe taking our ideas of motion in 2 dimensions and multiple objects to just another level. Okay, that's it for me for this lesson. Hope you guys are staying well. We'll see you soon.